Hello,
Okay.
everyone. I'm Alex. I'm hosting the zkStudyClub today. Anna is with us, but she's out and letting me take the lead here. So we are very lucky and fortunate to have Pratyush Mishra of University of California, Berkeley, and Benedikt Bünz from Stanford University here presenting proof-carrying data without succinct arguments. So with that, I'm going to pass it over to the speakers, Pratyush and Benedikt. Thank you very much for being here, guys, and take it away.
Awesome. Yeah, hi, everyone. Thanks for having us on. Yeah, so today I'll be presenting a paper, Proof Carrying Data Without Succinct Arguments. This is joint work with my excellent co-authors, Benedikt, Alessandro, William, and Nick. Benedikt will also be presenting in a later part of the talk. So this paper is online at this URL, and the code we have an implementation, and the code should be online soon as well. Okay, so let's get started. So yeah, the primary motivation of this kind of work is to delegate some t-step non-deterministic computation, right? So let's say you're given some function f and some initial input and some final output. What you want to do is to be able to check that there exists some intermediate inputs, z1 through zt minus 1, and some intermediate witnesses, w0 through wt minus 1, such that f applied to the input at this step and the witness at this step outputs the input for the next step, so zi plus 1, right? And this should hold for every time step t, right? So it's basically just an iterated application of f on z0. Okay, so there's multiple ways to do this. This perhaps simplest way is a monolithic proof, right? Where I just produce a single proof for the computation, which is f applied t times on a z0 with w0 through wt minus 1 as witnesses, right? And what I check is that f applied t times gives zt, right? So I prove this and I get one small proof. Now, this is a simple approach, but the problem is that it requires a large amount of prover memory. So it's s times t, where s is the space required to compute f. And furthermore, if you want to now produce a proof for additional t plus 1th step, this requires redoing the entire proof from scratch. You can't easily reuse most of the computation that you've already done, right? So to resolve this problem, people have developed this notion of incrementally verifiable computation, or IVC. And the idea here is that you incrementally prove the correctness of each time step. So you, at the 0th time step, the IVC prover p sub f, it takes in z0 and w0 and then produces the next step input z1, along with the proof pi1, which attests that f applied to z0 and w0 gives out z1, right? And then at the next step, at the 1st step, the IVC prover takes in pi1 and z1 and checks that f is applied correctly, but also that pi1 is valid. So basically, at each step, you check that the previous that the proof for the previous step is valid, and you check that this step's computation is performed correctly. And you can continue this indefinitely until you are satisfied. Okay, so this is a useful notion. It's also been generalized to proof carrying data, where you, instead of just doing a single line graph, you can prove the correctness of computations along any DAG. And this has many applications, particularly in the blockchain space. So one application is succinct blockchains, where you prove the correctness of the transition function of your blockchain. There are applications to constructing SNARKs, which have low space complexity, to constructing verifiable delay functions, and even to improving the efficiency of Byzantine agreement. Okay. So this seems like a useful primitive, but how do we actually construct IVC or PCD? And so far, like the best constructions we know, you rely on SNARKs, right? Where a SNARK is just a succinct non-interactive argument of knowledge, so a very short proof, right? So the original approach for constructing IVC from SNARKs relied on SNARKs with succinct verification, which means that it's at most polylogarithmic in the circuit size of the complexity of f, for example. This was recently relaxed to just require sublinear verification. So even square root n, for example, could suffice. And then building on ideas from Halo or BGH19, we propose how to relax this further by constructing IVC from SNARKs, where you don't have sublinear verification, but only sublinear accumulation. I'll explain what accumulation is a little bit down the line. Right? So the question we want to ask wanted to ask in this work is, it seems that SNARKs are essential, but are they actually required for constructing IVC? And in some sense, the answer is yes, because IVC does imply SNARK. So if you have a construction of IVC, you can construct, as I said, the low complexity SNARKs from that IVC, right? But what we want to do is we want to ask whether we can construct IVC from something that's qualitatively weaker than SNARKs, right? Maybe just a non-tractive argument of knowledge. And any such construction, I mean, it would be, first of all, interesting just because it would be a new kind of construction entirely. But it could also have potentially better efficiency properties because, SNARKs are still quite technically complex and getting them efficient requires a lot of work, right? So you could get maybe better efficiency properties as well as maybe simpler constructions, right? So maybe we can do away with all the heavy machinery that SNARKs require. Right. So I'd like to know there is a different construction of IVC, but it has some limitations. So I won't talk about it further here. Right. Okay. So to summarize our results, what we achieve in this paper is we introduce a new cryptographic primitive called the split accumulation scheme. And we show that you can construct IVC from a zero knowledge non-tractive argument of knowledge, no succinctness, as long as that non-tractive argument of knowledge, or NARC, has a split accumulation scheme, right? And if you have zero knowledge, then your IVC scheme also inherits the zero knowledge. Right? So there's a slight asterisk. I'll get into what that asterisk is a little bit later, but roughly we move the succinctness from the NARC to the accumulation scheme, or one component specifically of the accumulation scheme. Right? Okay. So that's a generic construction of IVC from these NARCs with split accumulation. But can we actually construct, these NARCs? And what we do is we show that assuming discrete log and random oracle, in the random oracle model, there is a zkSNARK which has a split accumulation scheme for the R1CS relation, where the accumulation verifier performs only a constant number of group scalar multiplications, field operations, and random oracle queries. So looking down the line, what this means is that the recursive circuit only contains O of 1 constant number of all of these operations, right? And this is in contrast to BCMS20 and also Halo, where the complexity of all of these operations is logarithmic, where here n is the size of your constraint system. So yeah, we get a big improvement asymptotically, and also, as we'll see in practice in our implementation. So theorem 1 only applies in a standard model, which means that you can't have random oracles around anywhere. But for theorem 2, we only know how to actually construct these things in the random oracle model. I'll explain this in a little bit more detail right after this. So I want to clarify that just like the notion introduced in BCMS20, split accumulation schemes have nothing to do with set accumulators. Rather, they sort of accumulate the correctness or membership inside a relation in some sense. Okay. Yeah, so we implemented and evaluated this. I'll dive into this, a few more details about this soon. Okay. So to summarize our theorems, right? So what we prove is that if I give you a NARC and a split accumulation scheme for that NARC, then I can construct an IVC scheme. And then applying the theorem in BCCD13, this allows us to get zkSNARK. So this is, it seems kind of counterintuitive, right? You start with a weak object like a NARC, and then you can apply this series of transformations and get out a SNARK, right? So, that personally to me, that's pretty cool. Right? But the problem with this, I guess this picture is that we don't know how to instantiate this in the standard model. And theorem 1 only accepts things in the standard model. So what we have to do is to settle for heuristics, right? And so what we have to do is that we construct a very simple non-tractive argument of knowledge for R1CS, right? And then we construct a split accumulation scheme for that argument of knowledge in the random oracle model, right? And then we instantiate the random oracle heuristically and obtain this accumulation scheme in the standard model. So you can imagine just replacing your random oracle with Poseidon or Blake 2s or something, right? So we can't prove that it acts like a random oracle, but it's probably good enough for our use for practical purposes. right? And then now we can apply a theorem 1 to get new IVC and PCD constructions. Of course, heuristically, but the heuristic is just in the instantiation of the random oracle. Everything else is provably secure from discrete logs. Okay, so this is without zero knowledge. And then with zero knowledge, it gets a little bit more complicated. Now, both the NARC and the accumulation scheme actually are in the random oracle model, and then you have to instantiate the random oracle. And the cool thing is that the zkNARK, it's actually under the hood just a Sigma protocol, right? And then we can apply standard fiat-Shamir and then instantiate the random oracle to get out.
So hang on, just go over again how the zk case differs from the non-zk.
Yeah, it's a great question. Maybe I went through that too fast. But in the non-zk case, you actually don't require any random oracles for the NARC. It's actually, at some level, you're just sending the R1CS witness. We'll see just in a little bit more detail later on in the talk. But there's no random oracle here. So the only place a random oracle appears in the non-zk construction is in the construction of the accumulation scheme, and not in the construction of the NARC.
Okay.
The only place we need to introduce the random oracle for the NARC only to achieve zero knowledge. Yeah, so as you'll see here, so we start off with Sigma protocol, which is zero knowledge, and then we apply fiat-Shamir in the random oracle model to get a zkNARK for R1CS. And then we have to instantiate the random oracle to get something in the standard model here. But if we didn't care about zero knowledge, then we would just, the NARC itself would be entirely in the standard model, and only the accumulation scheme would be in the ROM.
Okay.
Okay. All right, so does that clarify the our contributions on the theoretical front? Are there any questions so far? Okay, cool. Right, okay, so this is, so it's nice to have like a simple construction, right? It's just a Sigma protocol, they're simple to analyze. But, sometimes in the quest of simplicity, people, constructions sacrifice efficiency, right? But what we show is that, all our constructions actually give better efficiency. So in more detail, we implemented PCD from both atomic and split accumulation as part of the ARC PCD library, which should, these updates should be available online soon. This library already contained an implementation of the BCTV approach, which is recursion based on pairing-friendly SNARKs, like Grok16, right? And the nice thing about having all of these implemented in one library is that it allows us to compare the cost of PCD across all of these different paradigms so far, right? So these paradigms, namely being BCTV, which is cycles of pairing-friendly curves, which are rare. So you need trusted setup, but then you get constant size recursive circuit, and at the end, constant size proofs, as well as succinct verification, right? The other two approaches implemented are the ones based on accumulation. So we have so-called atomic accumulation. I'll explain what that is. But this is like the approach from Halo and expanded on from BCMS 20. And this requires cycles of standard curves, but they have to be FFT friendly. So they have to have high two-adicity, right? But you get nice benefits like transparent setup. Now the recursive circuit is slightly larger, and the proof verification at the end is linear. And finally, we also have implementation of the schemes from this work. And now this allows us to use cycles of standard curves. So you don't have to have any two-adicity requirement. What this means is that you can use cycles like the SegP cycle. So this could be useful maybe for Bitcoin applications, right? So there's a cycle involving SegP, so you can maybe do some recursive composition or recursively proof facts about the SegP, operations over SegP, right? And we still have transparent setup, and now the recursive circuit is constant size. And in particular, it has as few as 4 scalar multiplications, which is tiny. Right. And so we implemented this, and we compared the cost of all of these different schemes, and we found that our approach offers even lower recursive costs than taking the approach of BCTV14 over Grok16. Right. So even with pairing-friendly, circuit-specific pre-processing SNARKs, our approach is as a smaller recursive circuit, which a priori you wouldn't think would be the case. Now, of course, we pay for this. There's no free lunch. And we pay for this in terms of larger proof sizes, but there are ways to work around this depending on your application. Okay, yeah, so I'll cover, again, more detail about all of these things later on in the talk, but yeah, I just want to stop and ask, before we dive into the technical part of the talk, if there's any questions on any of the stuff that I've talked about so far.
So the proof sizes, so you have a constant size recursive circuit, and your proof size is linear in the size of the circuit.
Yes.
So technically, I suppose your proof size is constant. But you would have to split up your application circuit so that it fit within the recursion bound to take advantage of that. Is that right?
Right. It is constant. Yeah, oh, go ahead. Sorry.
Okay. So yeah, yeah. So basically, the idea is that we split up our proof into a small part, which is the only thing which goes into the recursive circuit, and then a large part which does not go inside the recursive circuit. But at the end, to verify the proof, you need both of these components. Like the final proof outside the circuit, when you want to verify the IVC proof, you do need to have both of these components. And that's basically how we work around by, like, we don't put the linear portion inside the recursive circuit, and that's how we get this constant size recursion.
How feasible would it be to do a proof at the end, which was basically verifying the linear time part of the verification?
So it should be
doing that using a succinct proof system.
It should be entirely possible. In particular, like, so for example, with the application to the MENA application, right? When you want a succinct blockchain, at the end, for the light client, you want to send a small proof, right, for the state so far, and then you could for the final computation of the decider, as we'll see, it's actually just checking a sort of multiscalar multiplication at a high level, and that portion you can you should be able to do just as part of a decider, as part of like a inner product argument, for example.
Okay.
And yeah, I think it might require a little bit more work, but it should be possible.
I mean, so I mean, you have to kind of, there's multiple roles even in PCD where you definitely need the entire proof or the entire state in order to, right, like PCD or IVC says one key property is that you're able to continue the computation, right? That, like, given a proof, you're able to continue the computation. And for that, you need to see the entire proof. But that's, even if you use something like BCTV, right? Like if you use the Gross 16 BCTV, right? You oftentimes are like the succinct blockchains, you need to know the provers, they need to know the internal state of the blockchain anyway, right? There's some state, some account state, and they need to know that in order to do something useful with it. And so in order to continue the computation, to add a block, or to add a computation step, yes, you do need to know the proof. If you just care about verifying it, then you could outsource this decider using some other proof system. Say, like as Pratyush was saying, you can do an inner product argument to make this, like, practically very efficient.
But so suppose you end up with a succinct proof, then you can use that to bootstrap another instance of your scheme. So you wouldn't need the state from your scheme. You're periodically you're compressing that state. Would that work?
Right, but then I think you would run into some. So then at some point you have a logarithmic size recursion circuit. For example, if you use the Halo approach, at some point you would have a logarithmic size recursive circuit somewhere in the middle, which maybe it's fine. Like you just do it one time and then you continue the proof step using this constant size recursive circuit thereafter.
Yeah, it would only give you a constant factor improvement, I guess, depending on how many of those intermediate compressions you need.
Right.
Okay, carry on.
Okay. Oh, yeah, thanks for the question. Okay, if there are no other questions, then I'll hop into the technical portion. We'll start off with, what the recent advances in IVC and PCD have been. Namely, I'll talk about how we've been constructing recursive composition using atomic accumulation schemes. Okay. So, before we dive in, what is IVC formally, right? So there's two parties, a prover and a verifier. The prover, it takes in the previous or the current state input and a corresponding witness, and proof pi for the that attests to the correctness of the computation thus far. And then it produces a new proof, pi prime, which ensures that f applied to z comma w results in z prime, right? So this is what the prover does. It produces a new proof which attests to the correctness of all the previous computation as well as the correctness of the current step. And then the IVC verifier, it takes in the final proof pi along with the initial input z and maybe the final output zt, and decides whether or not the proof is valid, that it corresponds to a correct history of computation. So the idea with IVC is that you can continue propagating this computation over time. So you can feed in z prime again into the prover and pi prime again into the prover along with the new w prime, and then produce a new proof pi double prime and so on. Right, so the properties we want are completeness, which means that basically you can keep extending the chain. So if the current proof is valid, then an honest prover can take that valid proof and then prove the correctness of the next step in the computation, right? And for proof of knowledge, what we want is that if the verifier accepts a given input comma proof pair, then we can extract from that adversary complete transcript of the computation so far. So basically, all the intermediate state we can extract it, and it'll correspond to a valid sequence of computation steps. Okay. The efficiency property we want is that the proof size should not grow with the number of computation steps. Right. So this means that it should be equal across the invocations of the prover. All right. Okay. So that's IVC. Now we'll talk about the other key component of this talk, which is a SNARK, or in particular a NARC, right? So SNARKs are defined for particular relations. In this, part of this talk, we'll focus on the arithmetic circuit satisfiability relation. And the idea here is that there is some indexer which takes in some public parameters and pre-processes them to be circuit specific, and it produces a proving key and a verification key. The prover gets the proving key, and the verifier gets the verification key. And the prover can then take PK along with a public input X and a witness W and produce a proof that X comma W satisfies C. And the verifier can take VK X and then pi and check if pi is actually a valid proof, that there exists some W such that C of X comma W is 1. So the properties we want are completeness and adaptive proof of knowledge. Completeness just says that if I do have actual X comma W such that it satisfies the circuit, then I can produce a proof. And proof of knowledge just says that I can, if I accept the proof, then there must be some underlying witness that I can extract. Optionally, you might want sublinear proofs and sublinear verification, which means that the proof size is much smaller than the size of the circuit, and the verification time is much smaller than the time to compute C, right? And also zero knowledge, which just means that the proof reveals no information about W except for the fact that the circuit is satisfied. Okay, so this is a whirlwind overview of IVC and NARCs. So let's see now how we can construct IVC from succinct Nox or SNARKs, right? So the construction is very simple. So the IVC prover, first it invokes F on the input ZT to produce the next step output ZT plus 1. And then it constructs a recursive circuit which contains F as well as a copy of the SNARK verifier V, right? So this recursive circuit, it checks that F was applied correctly, namely that F of ZT equals ZT plus 1. and that the SNARK verifier accepted the previous step proof, pi t, right? So it checks these two computations, and then the IVC prover, it invokes the SNARK prover on this recursive circuit R to produce the next step proof, pi t plus 1, right? So at a high level, all the SNARK all the IVC prover does is that it constructs a SNARK proof which attests to the fact that the previous step computation, the previous proof is valid, and that this step computation is correct, right? Okay, the IVC verifier then it just invokes, it takes the final proof and the initial and final outputs and checks that the corresponding proof is valid, that pi t is valid. It just invokes a SNARK verifier on that. The properties you want are completeness, right? So completeness follows from this, the completeness of the SNARK. And soundness, or proof of knowledge rather, the basic idea is to recursively extract the transcript using the SNARK knowledge soundness. So step by step, I go backwards in time extracting witnesses, right? And I can only do this there's like some caveats. I'm doing this, and in particular, you require the SNARK for PCD at least. You require the SNARK to have a very strong a knowledge property, which I won't go into more detail here, but you can see the paper for information about that. Okay, so this construction is very simple, but there's two caveats. First of all, it doesn't hold in the random oracle model due to non-black box use of the SNARK verifier, right? Because you can't have oracles in your circuit, right? And the efficiency is that, so pi is just the size of the SNARK proof, and it places restrictions on the kinds of SNARKs that we can use, right? So what we need is, because we're proving statements about the SNARK verifier, then when the SNARK verifier, you express it as a circuit, it must be sublinear in the size of R. So a verifier for R must be sublinear in the size of R, right? So this means that you necessarily need to have sublinear verification for your SNARK, which limits the kinds of SNARKs that we can use.
Can you just go into a bit more detail about that? Does not hold in random oracle model?
Oh, right, because basically, you are instantiating the SNARK verifier, right, as a circuit, and you're putting it inside this R. So at that point, there's no oracles anywhere, right? So you can't have.
Oh, yeah, of course, it's obvious. Right.
Yeah. Right. So where was I? Right. Okay. So yeah. So we need to have this. So what about SNARKs without sublinear verification? So this is where Halo and our work BCMS20 comes in. And the idea here is to use this new primitive called an accumulation scheme. In this paper, to differentiate it from stupid accumulation schemes, we call these atomic accumulation schemes. Right. So the idea here is that you have some sequence of queries Q1 through Qt, right? And what you want to check is that there is for some predicate phi, phi is satisfied on all of these queries Q1 through Qt, right? So this phi can be, a variety of useful things. It can be, for example, your SNARK verifier. It can be your PC evaluation proof checking algorithm, and so on. There's like probably a bunch of useful primitive predicates that you could have, right? But basically, what you want to do is you want to check that across time that the sequence of queries satisfies the predicate at each time step, right? This is what you want to check, and an atomic accumulation scheme is a way to do that. So the key object in this accumulation scheme is called an accumulator. This is not a set accumulator, just as a reminder. Just think of it as some opaque object for the time being, right? And then there's an algorithm called an accumulation prover, which takes in an initial accumulator and a query for this time step and spits out a new accumulator, which sort of accumulates both A0 and Q1. And the idea is that you can continue this, over all t time steps, incrementally accumulating the accumulators between steps, right? So at time step 1, then P will accumulate Q2 and A1, and so on and so forth until at the end you'll accumulate AT minus 1 and QT to get the final accumulator AT. Right? Okay, so this is the accumulation prover. There's two more algorithms. The first is an accumulation verifier, which checks that the accumulation at each step is performed correctly. It just performs some cheap checks, which basically to make sure that A1 is the correct accumulation of A0 and Q1, right? And you do this at every step again, checking that each new accumulator is a valid accumulation of Q2 of the input at that step and the accumulator from the previous step. Right? Okay, so let's say we've done this across t time steps. At the end, you have a decider algorithm, which takes the final accumulator and checks that it's valid. It doesn't take in any of the past state. It only gets the final accumulator and decides whether or not it is valid, right? And the property that we want is that, if all of the verifiers at each step accept and the final decider accepts, that it must be the case that the predicate would have accepted the conjunction of the predicate on all the inputs would be true. Right? And okay, so you might think, oh, this is not particularly interesting, but the key insight here is that the size of the accumulation verifier, it must be much less, or the cost of the accumulation verifier must be much less than the cost of the predicate phi. Right? So checking that the accumulation happened correctly is much cheaper than computing the predicate yourself. And furthermore, that this accumulator does not grow with t, right? So which is why the decider is basically equal to the size of phi. It's roughly, and it does not grow with the cost of or the depth of the number of things you've accumulated. Okay, so any questions about this atomic accumulation scheme? This is sort of the thing that people might not be most familiar with. Yeah, at a high level, the idea is that instead of checking the predicate at each step, I basically keep accumulating the queries and performing some cheap checks on the accumulation. And then at the end, once I have the final accumulator, I perform an expensive check, which is equal to the cost of, or roughly equal to the cost of the predicate. And the savings are basically that, t times the cost of v is much less, t times the cost of v plus d is much less than t times phi. That's the efficiency gain that you make. Okay, so if there are no questions, I'll go on and we can see how we can construct IVC from atomic accumulation. So note that this and this slide, they're both part of the prior work, PCMS 20. So yeah, not part of this paper.
And implicit in Halo.
Yes, and yeah, based off of the ideas in Halo. Yeah. Right. Okay. So how do we do this? How do we get this IVC construction? So yeah, there's two components. A SNARK, P, V. So the SNARK algorithms I'll denote in blue, and the accumulation scheme algorithms, and they'll be in this burnt orange or whatever. Okay, so we have the SNARK, and we have an accumulation scheme, PVD, for the predicate, which is the SNARK verifier. Right. So the predicate that we're accumulating is the SNARK verifier. Okay, so now what the IVC prover does is it takes in an IVC proof and for the previous step along with the input for this step. Now the IVC proof consists of a SNARK proof as well as an accumulator, right? And so we want to get out, the next input and the next IVC proof, and we do that as follows. We obviously first invoke F to compute Zi plus 1, and then we invoke the IVC prover, the accumulation prover, which accumulates AI and the new input pi I along with Zi and produces a new accumulator AI plus 1, which is the accumulation of pi I and AI, right? Okay, so this is how we get AI plus 1. And then to get out pi I plus 1, we construct a recursive circuit which contains inside it not the SNARK verifier, but rather the accumulation verifier, this bold V, right? And what this accumulation verifier checks is that the accumulation at this step was performed correctly. So it checks that AI plus 1 is the correct accumulation of pi I and AI, right? And so we have this recursive circuit which computes F and the accumulation verifier, and then we invoke the SNARK prover on this recursive circuit and get out our new proof pi I plus 1, which, together with the AI plus 1 gives us our IVC proof for the next step, right? So the key thing to note here is that there is no SNARK verifier inside the recursive circuit, only the accumulation verifier, right? So now what we've changed is that instead of having the SNARK verifier be sublinear, we need the accumulation verifier to be sublinear. Okay, so that's the IVC prover. The IVC verifier, it just basically invokes the decider on the final accumulator, and the SNARK verifier for the recursive circuit. Okay, so as I said, the recursive circuit no longer contains a SNARK verifier, which allows us to get rid of the succinctness requirement for the SNARK. Okay, so completeness follows from the completeness of the SNARK and the accumulation scheme, straightforwardly, and soundness. We still require the strong knowledge property on the SNARK because we still extract recursively from the SNARK proof. But we only require a weaker soundness property on the accumulation scheme. So we don't need to have any knowledge assumptions about the accumulation scheme. Okay, so that's the state of the art in terms of constructing Ivc construction so far, right? So we have Ivc from SNARKs, recursive SNARKs, and Ivc from accumulation. Okay, so I guess before we dive in there, so yeah, so as I was saying, the accumulation verifier must be sublinear, which means that these proofs, the Ivc proof, and in particular the SNARK and the accumulator must both be sublinear, right? Yeah, so this is a state of the art. Ivc from SNARKs and Ivc from SNARKs with accumulation, atomic accumulation. And what we do with this in this work is we introduce a new tool called split accumulation, and we use that to make Ivc cheaper. So for, I guess, the next few slides, it'll be Benedikt taking over. So I'll stop sharing, and Benedikt, I guess, can talk about those portions.
Okay, thank you, Pratyush. Let me see whether. Okay, great. You guys all see my screen? Are there, before I get going, maybe are there any questions to what Pratyush just discussed regarding atomic accumulation before we dive into split accumulation?
Oh, right, yeah, definitely, because split our work after this builds on the Ivc construction. So if there's any questions here, best to clarify them now.
Yeah. Otherwise,
if anyone has questions, feel free to type them in the chat too, and I can verbalize them.
Okay.
It's worth noting, by the way, that in practice, you need to instantiate this using cycles of curves, and that makes things a little bit more complicated because you're basically alternating between two curves at each step. So
right, in practice, it seems like you bet accumulators, one for each curve.
yes, exactly.
Good point. Okay, so I'll go on and talk about split accumulation now. And in essence, what we'll be able to do is, right, it's kind of the last point that Pratyush made, is that the accumulation verifier must be sublinear. So both the proof and the accumulator must actually be short. They must not be efficiently verifiable, or the accumulator must not be efficiently decidable, and the proof must not be efficiently, or does not need to be efficiently verifiable, but these things need to be small. And what we do now is we show how we can actually get rid of this requirement, and this opens up, sort of the whole idea of this line of work that started with Halo is kind of, you relax the requirement of the tools that you need. And then in the end, you get kind of much better and much easier Ivc PCD from it. So we're really like trying to relax what we need to get out, the super powerful thing in the end, which is Ivc/PCD. So what is split accumulation, and in particular split accumulation for relations? So now let's consider, we are always talking about these predicates, and now let's consider that we have a relation, and for this relation we have an input Q, and this input can be split into a small instance and then a large witness. And the relation accepts if there exists a witness for an input. So we have an exists relation here. And let's say we have a bunch of these, and then we want to design an accumulation system saying that all of these output 1, right? So that for all I, there exist these witnesses, there exist these QWs. And again, think of the witnesses as being large and the instances as being short. But yeah, we want that all of them are equal to 1, evaluate 1. And what we're going to do now is we're going to build an accumulator for this accumulation for these relations. So what we'll do is, you know, it looks very similar as before. We'll have a prover, and the prover gets as input both the instance and the witness, and outputs a proof 1. And then, in fact, what we'll do is we'll also split the accumulator. So this is kind of, we're doing 2 things at once. We're splitting the relation input into an instance and a witness. But we can do kind of, you know, a similar thing to the accumulator, where we say the accumulator really consists of an instance as this witness. And now the difference is that the accumulation verifier, here again denoted by a small box because it needs to be very efficient, it only needs to receive as input the accumulation instance, the query instance, and then the proof that is created by the prover. So the prover has access to everything. It has access to a large accumulator, and the relation, the witness here. But the verifier only has access to the black things, which are very small. And the whole scheme is you know, it looks, it's still an accumulation scheme. So we still have this idea that we go from one accumulator and query here to a new accumulator. So we accumulate, you know, this old accumulator and then this input to the relation into a new accumulator. And at the end, there exists a decider, and the decider gets to read the accumulator. So the decider decides in the end, and it gets to read the entire accumulator. And the property that we want for the accumulation scheme is that if the decider accepts and all of the intermediate verifier, the accumulation verifier accepts, well then this implies that computationally it implies that all of this statement here below holds, so that all of the relations are evaluated 1. Okay, so the key difference here, right, is that we just simply, this is why we call it split accumulation, because we simply split our predicate and we split our accumulator into a short part and a large part, and then the verifier only needs to access the short parts. So the and still, you know, what should hold is similar properties as before with accumulation. We want that the cost of the verifier is much cheaper than the cost of the relation, and that the accumulator, the entire accumulator, does not grow with the number of accumulations. So now we've, you know, this is a more general accumulation scheme, right? You can, it's easy to see that atomic accumulation is just a subcategory of this, and in particular the one where the witnesses are empty. But it turns out that even from this more general accumulation, we can still construct IVC. So how does that work? So now let's assume we
Benedikt,
have
1 second. If you're writing on the slides, and I don't think we can see it.
Ah, okay, but you can see my pointer, right?
Yes.
Yeah, I'm just doing pointer. But now let's consider, let's say we have comma v is let p comma v now be a NARC. So what is a NARC? Well, it's a non-interactive argument of knowledge. So it's similar to a SNARK, but we completely drop the succinctness requirement. So there's no requirement anymore that the proof is short or efficiently verifiable. Of course, any SNARK is also a NARC, but it's not a requirement anymore. And then we have our split accumulation scheme. And for what relation in particular? Well, the relation says that we take as input some public input for the NARC, the accumulation instance, and then also the proof instance and the proof witness. So what we do is we take the NARC has a proof, and this proof may be long. So what we should be able to do is we should be able to split the proof into a short part here, and then a long part pi w. And that the relation that we are trying to accumulate is just simply the NARC verifier. So where the NARC verifier gets as input the accumulation instance, and then in Z, and also the entire proof. Okay. So yeah, we need to split. So the way that we now construct IVC from this is that we have our IVC proof, pi I alpha I, and then we put this into the, we create, we have our NARC prover. And now what is the recursive circuit that the NARC prover implements? Well, it simply implements the accumulation verifier, right? It again does this is similar to how we constructed IVC from atomic accumulation, where, sorry, my screen just went.
See you next time.
You guys don't do anything anymore, right? Oh,
I can't see anything.
I think my PowerPoint just crashed. Give me 1 second.
No problem.
Does anyone have any questions at this point? If so, perfect time to ask.
Perfect time, exactly. Okay. How do I start again? Share screen. Okay. Well, I think I mainly also lost my iPad. But okay. So, any questions? You guys see my screen again, right?
Yeah, we can see it.
Yep.
So in practice, how small can these small parts of the accumulator be?
Well, so both in theory and in practice, right? Like in practice, we want the small part of the accumulator to be as small as possible. Why? Because the accumulation verifier needs to read it. So it's a lower bound on how large the accumulation verifier is. In theory, what is sort of the smallest possible size that still allows us to construct IVC? Well, it's just basically anything that is sublinear, right? As long as the accumulation instance and the proof, if we can sort of split off a part that is sublinear in the size of the circuit that the NARC verifier is checking, well, then we are able to construct IVC from it. It just leads to a much larger recursion threshold, right? This is similar to, we can actually construct IVC from, this is what COS 20 showed, is that we can construct IVC from any SNARK that is sublinear. And here now, basically the only question is whether the accumulation verifier is sublinear in the size of the relation that it's proving. Does that make sense?
I see. So what I was trying to get at is for your concrete scheme that's in the paper.
Oh, it's like 4 group elements.
4 group elements. Okay.
I think
cool.
I think
so,
3 or 4.
Comparable...
For IVC, it's like 4, but like not for. Well, we'll see in a second. We're constructing, 4 group elements. We're constructing accumulation directly for R1CS, and for that you need. I think it's 4 group elements. Might even be 3. We can see in a second. We can count.
So it's comparable to the size of a Grot 16 proof.
Right, but there's no cycles of
but no pairings.
Yeah, no.
It's also even shorter because it's not one. Everything is just in the 255-bit group, so there's no G2 anywhere.
Yeah, so that's in 24 bits. Okay, thanks.
Okay, so now we want to construct IVC from it, and what we do is we simply create a recursive circuit, or we create the NARC prover proves that the accumulation verifier was correctly. And then this creates, this creates a new proof, which you then again feed into the NARC prover, and this is the same kind of recursive construction. And then in the end, the deciders, the IVC verifier simply runs the decider and runs the verifier. And I'm sorry, this is the old accumulation construction, and what we need to be careful here with is that, of course, we split up at every point here. We want to split up our proof into the large part and the small part, such that the accumulation verifier does not need to read the entire proof, right? It only needs to read the short part of the proof. And this is what allows us to use a NARC instead of a SNARK. So what do we need in order to prove soundness of this construction? Well, in order to prove soundness, we require that the NARC itself is extractable, right? Because in the end, you have only this one NARC verifier, which verifies the final proof. And what we want to do from this is we want to extract all of the previous proofs that were constructed. And additionally, we need that our accumulation scheme also now, this is a new property that we didn't have before, we need it to be extractable as well. So we need that even though the accumulation verifier only reads the short part of the accumulator, we now need that, we can extract the accumulation witness from whenever, we have an adversary that can convince a decider and an accumulation verifier. So from these strong soundness properties for both the NARC and the accumulation scheme, we can prove soundness for the entire IVC construction. And then the efficiency, importantly, is roughly the size of this recursive circuit, or it is dominated, or yeah, it's dominated by the size of the recursive circuit. But importantly, right, as I've already mentioned, it's independent of the size of the proof witness. So this can be really as large as we want it to be, and the accumulation witness. And then,
so how difficult is it to get this extra knowledge property?
It's not, I mean, it really depends on the construction. I mean, I think that sort of any atomic accumulation scheme, like already, like it trivially has this knowledge property, right? Because there's no knowledge, right? Like there's nothing, that I need to extract. Basically, there's soundness. There we just say soundness, there we just say, yes, this was kind of the implication that I showed on the first slide. And now there are these hidden parts that we need to say, right? There exists witnesses, so we need to somehow extract these witnesses. That's kind of, okay. And then how do we do it in practice for our schemes? Well, this is where Fiat Shamir and the random oracle heuristic comes in. So under the hood, these are interactive protocols, which we know how to, or basically we show actually that they have the knowledge property in the random oracle model. And then the problem is that we need to instantiate them in the standard model. So this is where heuristic comes in. But we show that they have exactly the knowledge property that is required in the random oracle model. So we prove this formally. So we say that we can construct IVC PCD from a split accumulation scheme. And in particular, what this means is that if we have a NARC and then we have a split accumulation scheme for this NARC verifier, then we get IVC PCD. And the cool thing, again, there's no sublinearity that is required. V itself, so the accumulation verifier, this is really what we care about. Like when you design one of these things, what you care about is the size, or is the efficiency of the accumulation verifier. And this must be sublinear, and we'll see we're highly efficient on that. And then, as I said, the NARC and the accumulation scheme must have strong knowledge properties. And we also prove that a lot of properties are kind of transfer over. So for example, if you want your PCD to be zero knowledge, well, then you need to actually require that both the NARC and the accumulation scheme are zero knowledge. And we also say that, we also show that if they are post-quantum secure, then so is the PCD. The particular scheme that I'll show is actually not post-quantum secure, but if you had a NARC and an accumulation scheme that were quantum secure, you would get a quantum secure PCD. And yeah, so we make non-black box use of the verifier. So again, the standard kind of heuristics that you need to do, we also need to apply here, because this does not hold in the random oracle model.
So has there been any work on seeing how to apply Frye-based polynomial commitments to this?
Yeah, I mean, I think the recent we also have an accumulation scheme for yes, there has been some work, but I don't know exactly what the state is. I mean, I think in general, there was this there was a recent we have also in this paper a split accumulation scheme for kind of a polynomial commitment scheme that just needs additive homomorphism, and there was a very similar result by it's called Halo Infinite was, I think, the name of the paper, and they show that it's even suffices if your polynomial commitment scheme is not linear, so it doesn't have additive homomorphism, but there's kind of this what do they call it, like a homomorphism check protocol. So as long as you apply this homomorphism check protocol, then you can do the accumulation. And they also show this for that something like this exists for Frye. So that would be the place to look.
Okay.
But I want to show you something, now, even if anything before was, I don't know, maybe too sort of too theoretical or too on the formal side, then I beg you to now pay attention again, because I'll present a split accumulation scheme for R1CS, and it's going to be extremely simple. And I hope that your takeaway is, wow, this is really simple. But what you have to remember is that all of the machinery that we talked about before and that we built allows us to take this extremely simple protocol and then construct something as powerful as IVC and PCD from it. In particular, I'll show you the special case for IVC, but we can also do this for PCD. So what we'll do is we'll design the split accumulation scheme for R1CS. So to recall, what is R1CS, or rank 1 constraint systems? So what we have is 3 different matrices, A, B, and C, and a vector X over a field. And this defines an instance, or ABC defines kind of the circuit, and X defines the public input to the circuit. And this is probably the most common language that is used to describe arithmetic circuits, both in theory and also in a lot of practical implementations. They use exactly this R1CS. And what we need to show to show that the circuit is satisfied, you need to show that there exists a secret vector W, such that for the concatenation of X and W, AZ Hadamard product BZ equals CZ. So this is the element-wise or Hadamard product. And as I already said, is you can take an arithmetic circuit and very easily, there's a pretty straightforward transformation to construct these matrices A, B, and C from it. And then the public inputs can be become the vector X. So yeah, it gives you a really good balance between structure and expressivity. And X is really important because it defines the public inputs, but for simplicity, we will simply we will ignore it in the future, but just be aware that we can actually make this work even if we don't ignore X. So any questions regarding R1CS, or is everybody familiar with it here. Okay, so right, all we want to show is this element-wise product, AZ circ BZ is equal to CZ. And what we can do is now I want to present to you a non-interactive proof of knowledge for R1CS. And the non-interactive proof of knowledge, it's, you know, years of research have gone into it. How do you construct it? Well, the prover just simply sends Z to the verifier. This is a non-interactive proof of knowledge for R1CS, right? Because what can the verifier do? The verifier just says that, well, it just simply checks whether AZ times BZ is equal to CZ, right? This is a completely trivial protocol, but it is a non-interactive proof of knowledge, right? It's a proof that the prover in fact knows Z because he sent Z, and it is non-interactive because there's only one message. There's no succinctness, of course. We'll actually use something a tiny bit more complicated, but all that we'll do is we'll commit to AZ, BZ, and CZ. So we'll use a vector commitment, like a Pedersen commitment, and commit to CA, CB, and CZ. And then the verifier additionally checks that these commitments are correct. And why do we use these commitments? Well, they will allow us to accumulate proofs, right? These are linearly homomorphic commitments, right? So if I add them, I have some linear, right? So for example, if I added CA plus CB, I would get a commitment to AZ plus BZ. And this will allow us to accumulate proofs. So this is the trivial non-interactive proof of knowledge, or NARC, right? There's no the A in NARC just says that there could be computational assumptions. Here, there's not even a computational assumption. So really, it's a non-interactive proof of knowledge. But this is going to be the basis for our accumulation scheme. And in particular, we want to accumulate now this NARC verifier. So we want to accumulate these checks on the right side and build an accumulation scheme for it. So here is the kind of the first attempt, right? And here we have on the right, we have the NARC verifier. So let's say our, right, we have our proof, and our proof consists of these commitments and the witness. And the way that we split up the proof, here now you can see it very nicely that there's a short part to the proof, namely these commitments. These are just 3 group elements. And then there's a large part of the proof, which is which is Z, the actual witness to the relation that we're trying to prove. Okay, so again, here's the verifier. And now our first attempt is to construct an accumulator, and let's assume that the accumulator does exactly kind of has the same form as the proof. So again, we can split it into these commitments here, and then an accumulator witness, which we'll call Y. And then the decider will kind of mirror exactly what the accumulation verifier does. Okay, so it checks that AY circ BY is equal to CY, and then the commitments are, that the commitments are all correct. So now we're going to try to accumulate basically these 2 things. So what we want to do is we want to take these 2 things, and ideally at the end we have a new accumulator, A prime, which has the same form as A, and yeah, and we'll have a simple protocol for accumulating it. So what is the first attempt to do this is we simply take a linear combination, right? Everything in this proof and in the accumulator is linear, right? These are group elements, so we can, there's a linear operation defined on them, and it's a vector of field elements, so there's also a linear operation defined on them. So what if we just take a random linear combination? So here we have a challenge beta. This will be generated through a random oracle, or if you want to think of it interactively, by the accumulation verifier. But in the end, yeah, we'll have this random challenge beta, and then we just take this linear combination between the accumulator and the proof. And so now what is, so what does, like, now let's look at kind of what we get out of this. So let's look at each of the commitments. So CA and CA prime, right? M is just placeholder for A, B, and C. So we take CA plus, let me actually get a pen here. Okay, so we take CA plus beta or CA prime plus beta CA. And now we evaluate what this is. Well, this is A times Y plus beta Y. And this is exactly equal to A plus, well, you know, this is right, we take the linear combination between Y plus beta Z, right? So this is exactly what we get here. So this here is equal to Y. Okay, now I'm writing with my mouse pad, which doesn't work very well, but maybe actually this could beta Z. Okay, I'll stop doing that. So it's easy to see that this exactly works out, right? You know, the commitments in accumulator prime are exactly what we need to be, what they need to be for CA, CB, or CA prime, CA, for CA, CB, and CC. Okay, so this kind of linear check we successfully accumulated. And then there's this other property, right, which the verifier and the decider check, namely that AY plus, or that A times, you know, our accumulation witness, circ B, our accumulation witness, is supposed to be equal to C times our accumulation witness. So let's expand on what A times our accumulation witness is. Well, our accumulation witness, again, Y plus beta Z. So we get AY plus beta times, we get AY circ BY plus beta times AY circ BZ plus B squared, right? This is, you know, this is, or actually, like, the first two terms are the ones that we really care about, right? AY circ BY, which is exactly the same check that we had done in for the proof, so by the Narc verifier. And then we have beta squared times AZ circ BZ. And then we have two cross terms here, right? Yeah? Was there a question? Okay, right. So we have, you know, kind of the checks that we care about here are the first check, and then with the beta squared coefficient, we have the check that was done by the decider, by the verifier, and this is done by the decider. And then we have a couple cross terms here. So this is exactly, you know, if we look at our matrix here, right, this is CY plus beta squared times CZ plus beta times junk. But unfortunately, this isn't quite exactly what we got from the accumulation, right? So what we got from the accumulation was C times A prime witness, which is C times Y plus beta C times Z. So we're almost there, right? We would have liked the beta squared term here, and then we have also this junk term here. So this didn't quite work, but, you know, we're almost there, not too far off. So any questions regarding this? Or I guess you want to see the solution?
Okay. Yes, please.
We're on the edge of our seats.
So the solution is that in the accumulator, we actually need an additional element. So we'll have our commitments to ZA, ZB, ZC, and then we need this additional commitment to the Hadamard product. Okay, so this is our C circ. Or CO. So how does it work now? So now the decider, so the verifier still does exactly the same thing, and then the decider still checks that CA prime, CB prime, and C prime are the correct commitments to AY, BY, and CY. But now we have this additional commitment. So this is not, the accumulator now is not an R1CS instance, in fact. right? We just have this additional commitment, which says that, okay, this should be a commitment to AY circ BY, right? There's no requirement now anymore that for Y, that Y is an R1CS instance, so that AY circ BY is equal to CY. But as it will turn out, this is actually enough. So how does our accumulation scheme work now? Well, we still get our challenge beta, but we'll have this additional element, C proof, C pi. And C pi will, if you look back at the protocol before, where we're not too far off, C pi will exactly commit to all of these junk terms, right? The cross terms before, and we can commit to them before knowing beta, right? These are fully determined before knowing beta. We just don't know the beta terms. So we can commit to junk before knowing beta. And this is exactly what we'll do. So we'll create this element C pi, which is the commitment to these cross terms. And then exactly junk. So then what we'll get is that our accumulator is equal to A prime X, and we still take exactly the same linear combinations between A prime and beta CA and B prime and beta CB and C prime and so on. And for the witness, we also take exactly the same linear combination. But now we also have the CO prime element, which will be in fact, exactly what we need it to be. So it will be A times Y prime, circ B times Y prime. And what the verifier can now check is that CO prime is equal to CO. So the old accumulation, the old accumulator element, plus beta squared times C, so this comes from the proof, plus beta times the junk term. So what the verifier checks is that, let's go back to the previous slide. So it checks that, exactly this relationship here, this in the middle. So let me get my laser, so that this thing here holds, right? So, and it can do that over the commitments because we committed to everything beforehand, right? Everything that it needs to know is committed to beforehand, namely CO, CC, and then our proof. So this C pi becomes the accumulation proof. So are there any questions regarding this protocol?
Need to stare at it for a bit.
Okay. What I want to say is, okay, what we can do is, right, so so what does the accumulation verifier need to do? Well, the accumulation verifier needs to compute A prime X, which are these three steps. And it also needs to compute CO prime, which for which it simply does this, performs this check. So we can count the number of exponentiations that the accumulation verifier needs to do. And so we have one here, one here, so 2, 3, 4, 5. So it needs to do 5 scalar multiplications in this group in order to perform this. There's an optimization where you can actually combine CA and CB into a single commitment, and then you get from 5 to 4. So
you can actually even reduce it further. You just take in the CO prime check, you can just take beta common for the last 2 terms.
You take beta, say again?
You just take beta common for the last 2 terms, and you've already computed beta C, right? So then you just, it's like even 3, I think, scalar multiplications. With all the optimizations.
We've even just got it down to 3 scalar multiplications, and we can maybe even use smaller challenges to optimize things, and there's a bunch of tricks. But in any case, you have to really do it's what the accumulation verifier does is extremely trivial work, and this is important, again leading back to kind of the first part of the talk, because all we put into the recursive circuit is this accumulation verifier.
Yeah, so these challenges can be short. Is there a tight security proof that tells you how short they can be?
There's I mean, well, part of the security proof is heuristic because we have to, but I don't want to say anything wrong.
That's fair.
I do believe that it's possible to extract a fairly tight security proof.
Yeah, because I know there's the recent proof of bulletproofs that was tight, much tighter than I expected it would be. So you can maybe apply the same techniques.
Yeah, to be honest, I don't want to say anything wrong. So we haven't put a particular focus on giving a tight security proof, but yeah.
So that's what you would need to minimize the size of the challenges.
That is true. Yes. Wait, are there any? Sorry, I keep skipping ahead. Any more questions regarding this protocol?
So I wonder, by the way, sorry for the noise before phone bugs. I wonder, this question may not make total sense because if there's some sort of threshold where, right, this is super simple, and right, I guess for a really small R1CS, this would be better than, maybe the verifier would be more, or prover would be more efficient than Groth 16 or another. Is there like some approximate threshold where if the R1CS is small enough and I'm doing recursive proofs on this small R1CS, then it's better to use this than the other stuff, like the SNARKs?
So the thing is that, right, like the key difference to say something like Groth 16 and so on is that it doesn't at all require FFTs, right? There's not a single FFT inside. I would assume that, like, to me it looks like it's always more efficient than Groth 16, like, or that at least the efficiency is kind of independent of the size in comparison to Groth 16. I mean, what you get with but of course, I mean, do I believe that you could maybe do better or probably do better with a trusted setup? I mean, yeah, of course, a trusted setup is always easier, it's but here we don't need a trusted setup, we don't need FFTs, and we get something pretty powerful. So
oh yeah, I'm saying maybe for small R1CS, this would be saying this.
I don't think even for small, I don't think it has anything to do with small or large. If like,
well, small, maybe if you take, you're saying prover, it might be always better. Yeah, I guess so. In terms of verifier, then the question is.
Well, okay, so I mean, the Narc itself is not very efficient because you need to send the entire, right? You need to send Z itself, right? So this is not an efficient, like, this is not a SNARK, right? It's just a Narc. But the powerful thing is that this still suffices to construct IVC from it. And yeah.
So yeah, that's what I'm saying, right? If I understand, if I followed correctly, and maybe right, if you're doing IVC with this or recursion with this, the verifier, the communication complexity will be like 1Z. Like if you're doing some recursive thing.
Right, at the very end, basically, yes, if you're doing a long recursive computation, at the end, you will need to send 1Z. And I think Pratyush will talk about some implementation numbers, but that's on the order of, what is it, like at the recursion threshold, it's like a megabyte?
Like for between 2 and 4 megabytes at the end. But then again, we can compress that a bit.
But so yeah.
Sorry, I just wanted to jump in. There are many metrics one can look at, right? If you were asking about the prover, then I guess we didn't try them head to head, but I would be surprised if there's any input size on which Groth 16 is better for prover. Just because Groth 16 is just as simple as it is still more complicated than this thing.
There's also like G2 computations and FFTs. So this is I would 100% bet that this protocol is faster.
And you also have to use pairing groups, which are larger.
Yep.
Exactly. But there is that part. So there's other metrics, like for example, the recursion threshold. That one we measured, and it is better than Grot16. The main point where there is like an enormous difference is, of course, the proof size and the verifier time. Both are linear here, and very soon they get huge in megabytes and maybe tens of megabytes if you get pretty big, right? Whereas in Grot16 that doesn't happen. And of course you can compress them away, like on the side, outside of the recursion. But that is this is a tool that is completely made for recursion and nothing else, basically.
And right, the final proof size and verifier time, they don't depend on the depth of the recursion, right?
That's the key thing. They don't depend on the depth.
Right. So I think one interesting number is like what would be the R1CS size where you beat Grot16/Marlin/Planck in everything, also in proof size and verifier time, right? Probably if you keep recursing on a smaller R1CS, you'll beat the others and the SNARKs in all parameters. Maybe that's.
It's really the question what you mean by all parameters, but
verifier time and proof size. Yeah, because the others you easily beat probably.
No, but because just reading a several megabyte proof is going to be expensive, and
I know, but it's several megabytes when the R1CS is large enough. No,
right. So to get it down to like something that is manageable. So like let's get some concrete numbers. If you want, even like R1CS has 1,000 constraints, which is less than the cost of a scalar multiplication. Then it's going to be like 32 times 1,000, which is like 32 kilobytes just for 1,000 constraint R1CS, and that's already larger than Planck over KZG, Marlin over KZG, Planck, and any of these systems over these IPA-based polynomial commitments. So I don't think it's like a point at which, any reasonable point at which recursion will lead to give you like a smaller overall proof size compared to Planck or Marlin or Halo or any of these systems. I think it's more a matter of like when you find your application, then you can do some application-specific tweaks to make sure that at the end, maybe you can compress it via the techniques that we were discussing earlier. You use some SNARK to prove the decider is correct at a high level.
Mm-hmm.
But that's like application-specific.
Yeah, maybe we can continue the discussion on concrete numbers when Pratyush will present them in a little bit.
Just one more thing. So there might be scope here to use a square root proof size system. It's kind of a hybrid between this and the IPA-based systems.
Yeah, I think that's absolutely, you can. There's the inner product argument has different variants with. So yeah, I think sort of, there's a lot of interesting things you could still sort of combine with this protocol in the end to even make the final proof be smaller. But I think it also depends on your application, whether, that is something you need to do or you don't need to do, or yeah. But I'm going to continue now. So I guess, what I already mentioned kind of, and I hope people realize is that we are able, right? This allows us to construct IVC from two, very, very simple protocols. And there's no PCPs, linear PCPs, IOPs, and it's all right, like all this fancy machinery, not even FFTs inside. And what I think, Ariel is alluding to is that this actually does, you're right, this does give us a SNARK in the end, because an IVC gives us a SNARK. So basically from really trivial stuff, if we go all the way through our machinery, we actually get a very simple SNARK construction at the end. And I think we were already discussing concrete parameters on this SNARK construction. And yeah, there's a major caveat that, of course, we have to do a recursive circuit on a random oracle. So you have to it's right. There's a key difference between using a random oracle and like using Fiat Shamir in a protocol like say bulletproofs or Marlin or Plonk or whatever. And here, where we actually have to implement the random oracle then within the circuit, but at least we only have to do, there's only one query. And there's obviously an interesting theoretical question of if we can even get rid of that query, using collision intractable hashes or some other fancy tools, and it's not going to be easy, but it's certainly not out of the question anymore. And that would be a really interesting theoretical result. So the other thing is that, that I want to quickly talk about, and I'll try to go a little bit faster now because we're nearing kind of the end, is zero knowledge. So if we have a zk, what we need for zero knowledge is we need a zkNARK for R1CS. So basically what we'll do for that is we'll construct, you saw the super simple scheme, which was just a NARC. And basically we will turn that, in order to get zero knowledge, it becomes a Sigma protocol. So there's a very simple Sigma protocol. It's like what you would think of if you said like, if you gave as a homework to a grad school student, design me a Sigma protocol for R1CS, this is basically what we use. And then we also make our accumulation scheme. We also need to make that zero knowledge, and so create a zk split accumulation scheme for the zkNARK. And the ideas that we use for that are we use a hiding vector commitment, of course, and then we basically get, in order to get this zk split accumulation, we kind of have to also accumulate a random accumulator in addition to A. And so this actually makes our scheme a little bit more complex because the underlying NARC is more complex, and then the split accumulation scheme also needs to be zero knowledge. And so yeah, we this is makes the zero knowledge still possible, and we also still have the specialized protocol for, right? So if you look at the previous protocol, it was only a protocol for accumulating one accumulator and one predicate input. Yeah, we can make this also zero knowledge in a specialized protocol. We also apply this for the general case, right? So far, as I said, we accumulated one proof and one accumulator into one new accumulator prime. And if we want to achieve full PCD, we need to accumulate n proofs and n accumulators into one accumulator. And it turns out, in the past, whenever we've, all of the previous accumulation protocols that we looked at, they fairly trivially generalized. Here, this is actually not the case. So if we just try to extend the naive approach, we get messy cross terms. But we can build a 2-round accumulation scheme for Hadamard products. And to be honest, I'll skip over this. It's an idea that is very similar to something that was used in, say, the inner product argument paper and bulletproofs and Sonic. And we use a similar idea and for building a general accumulation scheme for Hadamard products. So yeah, I want to now hand over to Pratyush again, who will talk about the accumulation. And yeah, by the way, all of this kind of new stuff, it's not quite online yet. So the paper in general talking about split accumulation is online. This protocol for R1CS is something that we recently added, and I think we'll put out the paper, well, hopefully this week, or otherwise Ale will be very mad at us, but no, we'll put it out very, very shortly. And now Pratyush can talk about.
Is that going to be a new paper or
no? It will be the same paper. It will just be an update on ePrint, and
okay,
we'll tweet about it to let you guys know. So yeah, I'll stop sharing now to talk about. So Pratyush can talk about the amazing work they've done on implementing all of this.
Yeah, so I'll try to keep it quick because I know we're over time. So let me share my screen. Okay, so where were we? PowerPoint. Okay. Right. So yeah, we implemented. This is a very simple scheme, very pleasing theoretically, but also we wanted to test how efficient it is in practice. So we implemented a general framework for proof carrying data, which contains not only which contains a lot of, as I mentioned earlier, all the three different paradigms that are used in practice today. So first, this is not part of our work, but from a pre-existing implementation in this framework, we have the recursion via sublinear verification, which requires implementing a generic interface for SNARKs. So our PCD library is entirely generic. So you just give it, for example, a SNARK, and it'll spit out PCD based on recursion via sublinear verification. So BCD 14, right? And so into the generic interface for a SNARK, we plug in various components. For example, we have a recursion based on the Malin universal setup SNARK. We have also implementation. We also have recursion via Grot 16 and so on. Right, so this is not part of this work, but part of another part of my work, I guess. Then in terms of as part of this work, we implemented both of the accumulation, both of the recursion constructions based on accumulation and on atomic accumulation as well as split accumulation. So in terms of for atomic accumulation, we defined a sort of a generic accumulation scheme interface. And into this interface, we plugged in our various constructions of accumulation schemes, right? So for SNARKs, for polynomial commitments, and then constructions for the various PC schemes that people use, such as KZG as well as the inner product argument one, right? And the nice thing about our recursion, our construction is that it's again generic. So if I just give you a SNARK with atomic accumulation, any SNARK, any atomic accumulation, for that SNARK, you can just plug it in and have a construction. So it's like very modular. So in the future, if somebody develops even more efficient schemes, and it's easy to plug in and update and run it and get better numbers. And then we also implemented the schemes from this work. So within this accumulation scheme API, we made sure that we can handle split accumulation. And then we implemented in that our NARC as well as the accumulation scheme for that NARC, as well as accumulation scheme, split accumulation for a very simple polynomial commitment. And together, this is all based on top of various cycles of curves, but together this basically gives us a comprehensive framework for using PCD via any paradigm that you might care for. And this is all we hope to make it online soon as part of the ArcWorks ecosystem. This is at ArcPCD. This SNARK interface is part of ArcSNARK, and something wrong with the spacing there, but this is in a soon-to-be online library for accumulation schemes, Arc accumulation. Right. So yeah, the benefit of this is that, as I said, we can easily compare all of these different instantiations for efficiency. And with the application for IVC, we decided to perform this evaluation. What we found was that so if you take the BCDV14 construction with the state-of-the-art pairing-based NARC, Grot 16, once you add in all the overheads of hashing and so on and so forth, for the IVC case, the recursion threshold is somewhere closer to 250,000 constraints. This is partially just because there is overhead beyond the SNARK verifier, but also because we're using the MNT 46753 cycle, right? Which is 753 bits, and once you have scalar multiplications of that size inside your circuit, it's not cheap, right? So the benefits of this, at the end you get a very small SNARK, and it's generally efficient to compute the proof, but these pairing-friendly cycles, the MNT cycle, is quite expensive. Right. Okay, so then we also implemented the BCMS20 / Halo approach, right? And this is not the without the optimizations that the Halo folks have been doing. So it's somewhat, I guess, upper bound on the cost. Yeah, so the nice things are you don't have any pairing, so that reduces the complexity. You have medium-sized proofs. You know, they're not as small as cross-16 proofs, but they're, you know, at most a few kilobytes. And you can use standards, I guess, FFT-friendly cycles of curves. But yeah, but the downside is that now your recursive cost is quite large. It's larger than cross-16. Yeah, which can affect applications, because in the end, your verification time is linear, right? So what in this work when we implemented our simple NARC, and again, this is like with a generic protocol with you know, which supports arbitrary arity. So n proofs in and n old accumulators. For IVC, you can reduce this even further, I'm sure. So you get like a very low recursion threshold, but the problem is that now you have at the end large proofs. But maybe that's okay for your application, and as yeah, probably there's you can mitigate it in various ways. But the takeaway is that now you don't have to work with you know, pairing friendly cycles. You can just use standard curves, even like SECP based cycles, right? And you get a cheaper recursive circuit, and you know, at the end a simple protocol, which is, you know, there's a lot of, when you want to implement a SNARK, you have to take into account a lot of things. But with implementing our protocol, it's really a matter of, you know, everything together fits into less than 2,500 lines. So, yeah.
I'm confused about something, because the so for the Halo paper, which is we've optimized since then, the Halo paper had 17K constraints for the recursion threshold, if I remember correctly. Oh no, it was 2 to the 17, wasn't it? Yeah.
Yeah, 2 to the 17.
Actually,
yeah. So this is
2
our
to the 16. Sorry, yes, I got that wrong. Yeah, Halo 2 will be much less than that.
Right. So I think this is for our implementation in R1CS of the accumulation verifier. We've not done a lot of optimizations, like none of the GLV-based optimizations or, you know, special sampling of challenges or any of that.
I see. Okay. Yeah,
that
sounds about right then.
Yeah. So that's why like we have a relatively large cost here. So okay, this is also for. So yeah, the thing to note here is that there's not only like a, you know, a difference for some certain number of constraints, but also is a difference as, you know, increase the number or the size of the computation that you're checking, right? So this thing will grow logarithmically. So this is for like a circuit of size, and if the circuit that you're accumulating is of size 1 million constraints, right? But for the BCTV approach and for our approach, this cost doesn't change as you vary the size of the circuit or the computation at each step. So you can probably shrink this further, and you'll see like benefits as you decrease the, you know, as you add more optimizations, and this will also get lower. But I think no matter what you do, like you will not end up with like a constant number of scalar multiplications and field operations. I think this will always be, this might become eventually possibly slightly cheaper than this. I don't have any guarantees there, but I feel like it'll always be more expensive than this approach, than the
well, a lot of the optimizations that you can apply to for the 440 numbers also apply for the 65 number, right?
Yeah, exactly.
Yes. So the relative cost will sort of remain. Will exist.
In this argument that there is the exact same infrastructure underlying the second and the third column. So whatever optimizations apply to the orange, they apply to the green. So in particular, you know, if you want to delay scalar multiplications, you could do it on the left, you could do it on the right. If you want to improve, you know, the constraints for, you know, group arithmetic, it will affect the same way the left and the right. So,
I mean, you can argue that the reason that 440K is so large is that it's a 1 million constraint circuit. Did you say? So. Yeah. If you were to split that circuit up and use recursion, then it would be much less. So it would be 120 something thousand probably.
I thought it was
at the recursion threshold.
No, I think so. The cost, unfortunately, it grows logarithmically, right? So even if you split it in half, then it's still, we end up with like something closer to like 400K constraints for the recursion. For the cost of accumulation.
Right, but we did actually implement it for the Halo paper. And at the recursion threshold, it was 2 to the 17 constraints.
Right. So I'm sure there's quite a few optimizations that we can do. I think.
Yeah. I mean, it's only a constant factor difference, so I guess.
Yeah. I mean, there are like differences in terms of like what constraint language you're using and so on. But I guess the takeaway from this slide is not that the atomic accumulation approach is always going to be more expensive, but rather just that there is a both asymptotic difference, as well as I think the point is that the recursive costs, they both use the same kinds of operations, and if you optimize one, then the other one can also usually benefit from those.
That's true. And by the way, Plonk is very friendly to the kind of things you need in recursion.
Right. Yeah, especially for from the scalar multiplications becoming very much more efficient.
Yeah, I just want to understand a little. So this 250K, it's no accumulation schemes. It's like the cost of doing a pairing inside the circuit. That's the 250K.
Yes.
And the 440, yeah. So what? So that's what? Yeah. What? Can you say? Just remind me what's being done in these 440 constraints, like more or less.
So you're checking you're accumulating the inner product argument. So there's like log n rounds of I guess interactions, and log n scalar multiplications, O of log n scalar multiplications, and O of log n non-native field operations, and so on.
Oh, but they're non-native. Is I thought. Isn't this with this half pair something cycle pair?
Oh no, so this is not with a half. This is like with a standard like pasta cycle.
Oh, but it's still a cycle. So why?
Because in the end, you do have to do some sort of scalar field operations, right? In the sense that
it's worth pointing out that you get a factor of 2 just from using the endomorphism optimization.
Yeah, so we don't have that optimization. They should like halve the cost of the scalar multiplications. But then again, that will also apply for this case.
And the patent for it expired, right? Or something?
Sorry, what?
The patent for it expired or something?
Yes.
Yeah, last September or so.
Yeah. And then you get, so is this for full length scalars or for half?
We try to keep it as short as possible wherever we can. So 128 bits where possible.
Okay, so that's including the 128.
Yes.
So do you know more or less the relative cost, right? Because in this 440, I guess there's three. There's the scalar multiplications, and I guess there's this hashing to get the like random challenges. Do you remember more or less the part of each one in this 440? Yeah.
Yeah, the breakdown is dominated by. So you have like. Yeah, I think it's just dominated by the scalar multiplications and a little bit by the random oracle stuff. And there's actually no, the random oracle stuff is not that large. It's mostly due to the non-native. Basically, when you're doing the inner product argument, you're doing operations both over the base field of the constraint system, so the constraint system field, right? And this is, and the cycle allows you to make sure the curve arithmetic is efficient, right? But you also have to do, at least in our implementation, you have to do some work with the scalar field of the curve whose arithmetic you're checking.
Okay. So the Halo implementation completely avoided that.
So we didn't implement like this delayed arithmetic and delayed non-native arithmetic and so on.
That explains why it's so large compared to our implementation.
It's also the 65K is
also using that.
Well, it's also the general case protocol. So what I presented was the special case protocol for IVC, where you can get down to, I guess as Pratyush was saying, 3 scalar multiplications. This is the kind of general case protocol with n equals 1, m equals 1, and that is not quite as efficient. So that's probably twice, or like that's probably 7 or 8 scalar multiplications. So
so in that 65K, you are using sort of non-native field
arithmetic as yes.
Yeah.
How much of it? So how much of the 65K is that?
I haven't done a breakdown yet, but I would estimate it's probably close to at least 30-40% of the cost.
Okay.
Yeah.
Interesting.
And I think I think. Yeah.
So that's something where Plonk, even if you don't use the deferred stuff, then it's something where Plonk helps because you can use lookups for that.
Yeah. Yeah, I mean, to be able to use Plonk, I guess you have to move away from R1CS, and then, or maybe,
yeah,
I don't know. There's some.
You'd have to find a Plonk equivalent of the simple NARC.
Yeah. So
but I guess the thing is, moving away from FFTs, it does, for example, like the lookup stuff, a turbo Plonk, that kind of stuff, that really does rely on polynomials, it seems like. So there's downsides, obviously.
I'm not sure. So at first sight, it seems to depend on having the cyclic multiplicative subgroup, but I think it doesn't actually rely on that.
Okay.
Well, in the end, it's a permutation argument, no? I mean,
yeah, but you don't have to do the permutation argument on the full subgroup.
Right.
I only went.
Still permutation arguments, at least like the most efficient way to do them. Right. We don't have any polynomials in here, right? Like, so it's I don't know. Like I think obviously the main point, the only point that I wanted to make is that if we kind of said like one of the main goals of this paper was to think like, what is that simplest thing with the least requirement that still allows us to do IVC? And I think we've gone pretty far down that road. But obviously, if you sort of relax that back again and say like, okay, now maybe I don't care about, and maybe I'm okay with using FFTs, maybe I'm okay with, using some things, then you would hope that you would get better, because otherwise you're doing something wrong.
Yeah, and actually in the current version of the paper, we do have a NARC which relies on FFTs. So instead of using the Hadamard product, instead of accumulating the Hadamard product, we just check it via, the standard strategy for SNARKs, right? With the quotient polynomial and the vanishing polynomial. And so that one doesn't require, any of that, any of this, where did we go? Blah, blah. Yeah, it doesn't require, it doesn't require any of this machinery. So we just replace it with a couple of small non-native arithmetic multiplications. So that also further lowers the cost, for example.
Well, I think one thing that could be very interesting is if you could manage to get something, that's like this is very simple, and say just verifier proof size and verifier cost, say n over log n, right? If you could get some, or not as, maybe even, somewhere in the middle between as simple as this and the SNARK. And then, if you're doing recursion, then, do that thing for the original proof. And then, then recursively prove that with a SNARK, right? And then you'll get, maybe like even practical-ish linear time, because the recursive proof will be with FFTs, but on an n over log n thing. So that's, I think, maybe an interesting question here. Like, is there something almost, as simple as this, but that, does get you down a little, like to proof size n over log n, and verifier time n over log n.
Right. I mean, the question is like, do we want that, or do we just want to, what we can also always do, and what we've talked about is just the only case where really the proof size matters is at the very end. And, we know that we can sort of just outsource that, or, like maybe it's just efficient to outsource the verifier, instead, like at the end, give a SNARK that, that final verification check is correct. And then you might be able to get the best of both worlds. But yeah. But no, I mean, all very good questions and interesting suggestions.
Yeah, certainly a lot of.
Yeah, but just to, sorry, so just to like, is it, because I'm not sure. So say I don't really use recursion. I just want to sort of aggregate log n proofs or T proofs. Is the verification time and proof size then, but is the aggregation cost like going to be, like the proof size plus T, or is it going to be like proof size times T? Like the cost to sort of verify the aggregation. If I
You mean at the end?
Yeah, maybe I'm not saying, like, say it's not exactly like I just give you an advance T proofs of size N,
Right.
and I want you to
or whatever.
Exactly.
So it's going to be linear in the number of proofs because you have to read the proofs. But you can do this with Halo already. There's an efficient aggregation.
So if you do recursion there, so you can just do a recursion to do the accumulation verifier for the T size thing, and then at the end you only have it'll be T plus size of R1CS, just a little bit. So then you could do that. So just do one step of recursion, and that's sufficient.
So actually for Orchard, which is the next version of Zcash, we're using aggregation for Halo proofs, even though we're not using recursion, and that's just to reduce implementation complexity and auditing complexity. So that does work out very well in practice.
And guys, thank you. I've actually got to jump in here because we're a little bit over time. But this is a fascinating conversation and incredible work. So thank you. So just a couple things before we conclude. I'm actually just
let me just wrap up and just finish the last slide. We're in the last slide. So thanks. And the paper is it's online. It's like an older version, as Benedikt said. We will have an update hopefully just within the next week with these new protocols, as well as more details about evaluation and implementation, and hopefully more optimizations as well. So thank you, everyone.
Thank you, guys.